Alrighty, so now our last type of inference procedure for a parameter. Now we're looking at hypothesis testing for the difference of proportions. Now we may want to compare two proportions from separate populations to see if there is evidence that they are the same. We assume that they are the same and then proceed to use a significance test to see if we have sufficient evidence to support that they are equal. So for example, I could compare the proportion of right-handedness in males versus females. I could find evidence of the number of people who identify as Buddhist in East Asia versus West Asia, etc. So looking for differences in proportions here. Are they in fact the same, or is one greater than the other? So we're going to use the phantoms model here, but we're still going to use our state, plan, do, conclude. And again, the state will be the first two, plan will be the second two, and so forth. And I'll show you how I do that in my notes here. Well, we're going to state the parameters that we're testing. Here we're testing that the true population of proportion of group 1 and the true population proportion of group 2, we believe that they are equal. That's our initial claim. But I'm trying to find evidence that maybe population 2 is greater, or maybe it's less than, or maybe they're just not equal. There is some difference. So we're going to use an alpha level of 5% unless otherwise stated. Our assumptions do not change. Since we're doing two samples, the only addition here is the independence between the samples. So I'm still looking at random assignment, random sampling. 10% condition to ensure independence within each sample, some element of separateness between the two samples for my independence between samples, and then normal by large counts. Now what is going to be different is that we are going to check the pooled proportion. Now in the pooled proportion, you can actually find this on your AP Stats formula sheet. So on the back here, we're looking at two populations, and instead of knowing the true parameters, I'm just making an assumption about the proportions. So since we are assuming P1 equals P2, we're going to use this right here, which is called the pooled proportion. So P hat C is going to be the successes in both samples divided by the total of both samples added. So this looks a little bit scary, but I promise you it's not. So instead of checking the differences of the actual proportions like we were doing with the confidence interval, we're assuming the two proportions are equal. So I'm going to check the claim to verify the conditions, assuming that it came from the same population. But we know that they probably didn't come from the same population, and we're looking for that difference. Now, if our conditions are met, we will use a two-sample z-test for the difference of proportions. Now, our test statistic, again, this is based on the assumption that P1 equals P2. This is just the statistic, which is P hat 1 minus P hat 2, minus the parameter. Now, why is it 0? Well, we assume P1 equals P2, so P1 minus P2 is going to be 0. And then lastly, divided by our standard error using this P hat proportion here. Again, looks a lot scarier than it actually is, and the calculator will help check our work for us. Now, in order to obtain the p-value, we're looking for the relationship in the alternative hypothesis, either a less than or a greater than. And again, if it's a two-tailed, this is how you would do that, and I will show you eventually how to work one of those examples. Now, that will be our do step is the test statistic and the p-value. And then lastly, our conclude step will be making a decision and stating the conclusion. If the p-value is less than alpha, we reject the null hypothesis because there is sufficient evidence. If the p-value is greater than alpha, we fail to reject the null hypothesis because there's not sufficient evidence to support a difference in that claim. And we're going to look at one of my favorite examples, and that comes to us from the 2019 FRQ. And so tumbleweed, commonly found in the western United States, is a dried structure of certain plants that are blown by the wind. Kochia is a type of plant that turns into tumbleweed at the end of the summer, and it is a problem for farmers because it takes nutrients away from the soil that would otherwise go to more beneficial plants. Now, scientists are concerned that kochia plants are becoming resistant to the most commonly used herbicide, glyphosate. And in 2014, 19.7% of 61 randomly selected plants were resistant to glyphosate. And in 2017, 38.5% of 52 randomly selected kochia plants were resistant to the herbicide. Now, do the data provide convincing statistical evidence that at the level of alpha is 0.05, that there has been an increase in the proportion of all kochia plants that are resistant to glyphosate? So again, the order was not defined for us, but here I'm really testing, is the 2017 resistance rate greater than the 2014 resistance rate? So when I state my parameters here, this is what I want to do. I want to test that the null is that they're equal versus the alternative, which would be that the true proportion of kochia plants in 2017 resistant to glyphosate is greater than the true proportion of kochia plants in 2014 resistant to glyphosate. So notice here that I was reading my set of hypotheses, but I was using those in context of the parameter. So of course, I define what the parameters are first, P1 and P2, and then I write the relationship that I'm looking for. And here it says alpha is 0.01, but it should say alpha is 0.05. I hope that you'll forgive me. So let's look at our plan step, and this one is a little bit more detailed. We are just looking at our conditions. Now, the first condition, I have my sample size, I've got my P hat 1, so N1 and P hat 1 are both based on the 2017 sample, N2 and P hat 2 are both based on the 2014 sample. So I was told that I randomly selected 61 kochia plants in 2014 and that I randomly selected 52 kochia plants in 2017. So I can generalize to both populations. Next up, since I'm sampling without replacement, I can assume that both populations are relatively large. So again, here I use the inequalities, but you could say it is reasonable to assume there are at least 610 kochia plants in 2014 and at least 520 kochia plants in 2017. Next up, it is reasonable to assume that the samples are independent of one another since they came from separate years. There's a 3-year gap, so I'm thinking that my 2014 plants won't influence your 2017 plants. Next up is now the large counts condition, but now we're looking at these samples here. So I want to show you my calculations. So give me one moment here. Okay, so to compute the pooled proportion, again, I want to find x1 plus x2 over n1 plus n2. Well, you'll notice here that I'm multiplying two numbers, and those two numbers are p hat 1 and n1. And I'm doing this because I don't know the full successes yet, but I know that 19.7% of 61 randomly selected plants were successful. So if I calculate that, that's really about 12.017 of the 61 plants, and I would round to 12. And 38.5% of the 52 plants in 2017, one of them, are successful, and that'll be about 20 plants. So I changed them here to the integers, and I want you to include this step because when we put it in the calculators, I want you to see the successes over the total. So I do this, and I would get a pooled proportion of about 28.35%. So that's going to be the pooled proportion. So now when I check my large counts, notice that I'm checking N1 times P hat C. N1 times the complement, N2 and the complement. The reason being, since I'm assuming that the two proportions are equal, I'm going to treat it as the same success and failure rate, but I'm checking the difference in the sample sizes. So I would check here in my successes theoretically for the 2017 group would be 17.29, 43.71. And then I check for the 2014 group, about 14 and 37. All of which are greater than or equal to 10. So the normal model is appropriate by large counts. And since my conditions are met, I'm going to use a 2-sample z-test for the difference in population proportions. And you can write it symbolically or you can write it in words. Next up, we're going to go to the do step here. And this is, I'm just pulling this from my formula sheet, the statistic minus the parameter over the standard error. And I'm going to get 2.21. And since I want a greater than value, if I'm checking, again, using my z table, I would get about 0.0136. Now, I will show you how to do this in the calculator here. You're going to open up your calculator, and again, we're going to go to, not the documents, we're going to go to Scratchpad. We're going to select Menu, Statistics, and we're looking at a statistics test. Now, again, it's tempting to do a 2-sample z-test, but remember, we're looking at the difference of proportion, so it's a 2-prop z-test. You'll also notice that if you did the 2-sample z-test, you don't have any sigmas here. There's no standard deviations because we're looking at categorical data. So this is all based on counts. Well, we just saw that the success rate, if I get it from my notes here, this is why I calculated and I'm showing the work, because my success rate is 12. Yes, I know it's about 19.7 is the actual success rate, but the actual count of successes is roughly about 12. So that means when I look at that first group, and I'm sorry, my first group was the 2017 group. So I need to look here at the 38.5% from the 2017 group. Well, the successes for the 2017 group are about 20. And there were a total of 52 randomly selected plants. Next up, the successes in the 2014 group are about 12 out of 61 randomly selected plants. And I'm testing that the proportion in 2017 is greater than in 2014. If you do this backwards, you'll end up with the wrong sign. So we'll check our work here, and we get about 2.20954, and which we rounded to about 2.21. And the p-value here is about 0.013569, and we said about 0.0136. So again, we're just approximating. If I were to do it by hand, this is what it would look like, but here the handy dandy calculator verifies that we're not too far off. All right, now we need to conclude the problem. Since the p-value is about 0.0136, and this is less than our alpha value, we reject the null hypothesis. Thus, there is sufficient evidence to claim that the proportion of kochia plants resistant to glyphosate in 2017 is higher than the proportion of kochia plants resistant to glyphosate in 2014. Note that I'm making a decision based on the null hypothesis. Do I reject the null or do I fail to reject the null? Then when I give my conclusion, I am stating it in terms of the alternative hypothesis, right? There is enough evidence to support this, or there is insufficient evidence to support this. Now, the last sentence is not totally required, but again, this is just a real-world application of the problem. And here, we have reason to believe that there has been an increase in the proportion of all kochia plants resistant to glyphosate between the 2 years. So, long process, but again, the phantoms and the state plan do conclude model hold true, and there's just a few extra calculator steps. So what I need for you all to do now, and this one is a little bit different. This one comes to us from 2015. I want you to read this and go ahead and try it out on your own in your notes. And now this is a randomized experiment. And when we have a randomized experiment, we don't check the 10% or the independence condition because, remember, I'm just using volunteers. I can only generalize to people who are similar to my volunteers, so I'm not going to worry about the 10% condition because I'm only looking at this group of people. I can only generalize those results to people similar to those used in the study. Also, the independent groups, if you're getting one treatment and I'm getting another treatment, it's implied that those two treatments would not have influence on one another. So when we choose, when we're using randomized experiments, we only have to check the normalcy condition and the random assignment condition. So go ahead and read over this problem, give yourself about 10 to 15 minutes to try it out, and then we'll review the answers together. Alrighty, so we look here, and I'm stating that I'm going to test the null hypothesis that the two proportions are equal against the alternative hypothesis that P1 is less than P2, using an alpha level of 0.05, where P1 is the true proportion of people who would develop colon cancer given the aspirin, and P2 is the true proportion of people who would develop colon cancer given the placebo. So notice that here, instead of listing the parameters first and then the set of hypotheses, I listed the hypotheses first and then the parameters. As long as they're both stated there, you are good to go. Next up, using my planning step, I'm going to write some of the statistics that I was given, including the sample sizes and the sample proportions. And I check my first condition. I didn't use a random sample, I used random assignment. And so these 1,000 adult volunteers were randomly assigned to either the aspirin or the placebo group. Next up, I check my pooled proportion, and I get about 0.041, and I check the successes and failures in both the treatment group and the placebo group. And since all of them are at least 10, the successes and failures, the normal model will be appropriate by large counts. Next up, since our conditions are met, we will use a 2-sample z-test for the difference in population proportions. Next up, I will go to the do step here. And let's see, it looks as though we did P1 is less than P2, so I want 15 out of 500 and 26 out of 500. If I were to type this into the calculator again, so I'll go menu, statistics, stat test, 2-prop z-test, so I have 15 out of 500, and then 26 out of 500. And then we've got a less than here. We should get negative 1.75 and a p-value of about 0.037. So I'll check my notes here, and I get negative 1.7542. And again, remember, I use the z-table, so my p-value is going to be slightly different, about 0.04 compared to about 0.0396. Oh, comes out roughly the same, yay rounding. Well, let's conclude our step here. Since the p-value is less than alpha, we reject the null. There's sufficient evidence that the proportion of those who would develop colon cancer given the aspirin is less than that of those who would be given the placebo. And since this is a randomized experiment, the results are statistically significant, I can probably infer a cause and effect relationship. Also note that we just rejected the null hypothesis, and when we reject the null hypothesis, this would conclude in a type 1 error. Now that's going to wrap up our inference for proportions. We're going to practice in class, we'll use the calculator, and we'll do a little bit more. But in the next unit, we're now going to transition from proportions to quantitative data and looking at means. So stay tuned for inference for means.